All right. Okay, so now let's look at this geometrical cube. Yeah, and you get for every phase you can define the phase vector p alpha. So of course this I use the same label p. So you can imagine it actually relates to our flux. This is oriented area. So what is oriented area? So it means, namely, this is this vector. So the norm of the vector is just the area of the phase equals to area of phase of alpha space, alpha from 1 to 6, and the orientation of the vector is unit normal. Unit normal of phase alpha. Okay. So here, because this cube is in the Euclidean geometry, you definitely can talk about the area of the phase and the normal, unit normal of the phase. Okay. So once you have these 6 vectors, and it's easy to see that these 6 vectors satisfy a condition, satisfy a constraint. So you have so-called closure condition for these 6 vectors from 1 to 6, p alpha equals to 0. Yeah. The reason is that these vectors must satisfy this constraint because it is a closed. So all those 6 phases make up a closed surface. So 6 phases, because 6 phases form a closed surface. Closed surface. Closed surface. Yeah, which is the surface of this cube. Yeah, okay, because these 6 spaces form a closed surface, and you get this closure condition. Yeah. So this is the way. Okay, so you have the geometry, and you have a cube, and you have those phase vectors, and then these phase vectors satisfy this closure condition. Yeah, and you can make the argument converse. Yeah, you suppose you start with a closure condition, and you can determine the cube. Yeah, so there's a theorem proved that by Minkowski, the same Minkowski as Minkowski spacetime. So there's something called Minkowski theorem. Basically, it tells that the closure condition and geometrical cube or geometrical polyhedron is actually the same thing. This one is uniquely determined one from the other. So the theorem states that given n vectors, 3-dimensional vectors, p alpha from 1 to n. Well, this p alpha belongs to R3. Yeah, satisfy this closure condition. Satisfying closure condition. Sum alpha from 1 to n, p alpha equals to 0. Okay. Then there exists a unique polyhedron. Well, it can be tetrahedron, it can be cube, or any other polyhedron, depending on this n. You have this is the number of phases. Polyhedron in Euclidean space, in 3-dimensional Euclidean space, with of n phases. Number of vectors corresponding to the number of phases, such that p alpha is the oriented area. So this is the statement of Minkowski theorem. So here you can see that this closure condition and the geometrical cube is actually one-to-one corresponds to each other. Yeah. So now we can come back to our closure condition. So here this closure condition is just a closure. Here the Gauss constraint, this is just the closure condition. And this closure condition and respect to this pi, our flux, this is just a three-dimensional vector. And this is again a sum over 6 three-dimensional vectors equals to 0. And then this three-dimensional vector actually determines a geometrical cube. It is just a uniquely corresponds to a geometrical cube such that our flux equals to the phase-oriented area. Okay, so here we obtain that the loop quantum gravity closure condition so here sum over I and S P I V I S equals to 0 and is uniquely corresponds to a geometrical cube. Geometrical cube centered at V. Well, geometrical cube in Euclidean space centered at V, okay, such that the area phase oriented area P alpha equals to P V I S. So such that our flux can be identified to be the oriented area. Okay, so now so this is the classical geometrical interpretation of the closure condition or discretized Gauss constraint. Okay, so now let's come to the quantization. The quantum Gauss constraint. And so here here quantization of the Gauss constraint is the same as quantization of the closure condition. Yeah, but we know that from Minkowski theorem, the closure condition corresponds equivalent to the geometrical cube. So the quantum closure condition then it corresponds to a quantum cube. Means a quantization of the cube geometry. Okay. So now quantization means alpha from 1 to 6. From 1 to 6 P alpha vector P act on psi equals to 0. So this means a quantum cube, a quantization of the closure condition, or equivalently in terms of flux variable from plus minus 1 sum over I from 1 to 3 P hat J act on psi equals to 0. So we are going to solve this equation. Okay. So as we know that this flux operator is just proportional to the right invariant vector field. Yeah. And the right invariant vector field is equivalent to the angular momentum operator. And this is something we argued last time. Yeah. So now these flux equation, this closure condition, this is just equivalent to sum over right invariant vector fields. Minus 1, 1 to 3 in right invariant vector field. Operating on the wave function equals to 0. This is the equation we actually want to solve. Right, and because this right invariant vector field is just angular momentum operator, so this equation just means that the state is 0. The solution is just a 0 angular momentum state. 0 total angular momentum state. Angular momentum. 0 angular momentum state. Okay, so this is something we have already discussed before. So when we talk about gauge invariant wave functions, gauge invariant states, so the result we get is that those states are actually of zero total angular momentum if we formulate everything in terms of angular momentum. So it's like you have number of edges, it corresponds to the number of molecules, and each molecule has a angular momentum, right? Okay.
Yes.
All right. So here we see that we get a similar condition as we talk about gauge invariant wave functions. And indeed, actually, we just the solution are just those gauge invariant wave functions. How to see this? Okay, so because we can use the definition of the right invariant vector field, all right? So this is just given by the epsilon. Epsilon equals to 0. All the edges at vertex and psi, and you consider the left translation of your group element. Okay. So it means that you consider a simultaneous left translation of all the edges at the vertex, and then you take the derivative of the parameter. You consider the parameter to be the same for all the edges. You have 6 edges, and you make the left translation of holonomies of a group element on these 6 edges, and the left translation uses exactly the same parameter epsilon, and then you take the derivative of this epsilon. What you get is just the formula above. You get the sum, just the sum over right invariant vector field, and so the formula it just means this equals to 0. Okay, and obviously, so this left translation is just the gauge transformation. Can be viewed as just the gauge transformation at vertex B. At vertex B, because here we consider all the edges are outgoing. Okay, are outgoing. The left translation, where you multiply this group element on the left, it means that you make a gauge transformation at the vertex B. And so you consider this epsilon parameter to be the same for all the edges. It means it's really a gauge transformation. Okay, and clearly this equation is solved by gauge invariant wave function. Yeah, so because this is just a gauge transformation, and you taking the derivative of the gauge parameter, and the solution of this equation is gauge invariant wave function. Gauge invariant wave function. Okay, so it means that actually we have already obtained the solution. So this Gauss constraint we have solved already in our previous discussion. So our previous discussion just come to the gauge invariant, the Hilbert space of gauge invariant wave functions, and that those states already satisfy Gauss constraint. States satisfying quantum Gauss constraint. Span. They are just gauge invariant states. Span H gamma. So what is H gamma? They are Hilbert space of SU2 gauge invariant state. means H gamma. Okay, so here you can view that what we are actually doing is just quantizing. So of course we are doing loop quantum gravity. So we have the quantum Gauss constraint, and in terms of a sum of flux, and we know the flux operator is just right invariant vector field, and we know the solution are just gauge invariant states. Okay, and however, we can also consider just in terms of a geometrical cube. So what we are quantizing are just quantizing this geometrical cube. The quantization condition is replacing the oriented area by spin operator, by spin. Okay, and the solution is just the total angular momentum state. Yeah. And yeah, so these are total angular momentum states are just intertwiners, and intertwiners is the gadget where you enter these gauge invariant states. Yeah. The gauge invariant states are just T gamma J I, okay. And these I are just intertwiners, and intertwiners are zero total angular momentum state, and those intertwiners are just quantum cube quantization of this cube closure condition. Okay, so now we finished the Gauss constraint, which is very easy. So now let's come to other constraints. Okay, so the rest are quantum Hamiltonian constraint and quantum diffeomorphism constraint. And Hamiltonian constraint. Again, the idea is that you have Hamiltonian diffeomorphism constraint. You are going to quantize this operator, and you let this operator act on state equals to 0. And similarly for the Hamiltonian constraint, act on state equals to 0. And those are quantum constraint equation. You are in principle, you should solve them. Quantum constraint equations. Okay, so now let's come to the Hamiltonian constraints. So here, so we first talk about Hamiltonian constraint. It's a little bit more complicated than diffeomorphism. Well, but since we some techniques are shared by these two constraints. So when we first talk about Hamiltonian constraint, we learn those techniques, and then we are going to use them to the diffeomorphism constraint as well. So now let's first come to Hamiltonian constraint. So this is our expression for the Hamiltonian. Hamiltonian constraint. Recall the formula. That's point x minus 1 over kappa to Mn K B, and multiply a similar factor